Calculus BC, we are going to look at section 3.8, a very important section. Take a look at our learning target. I can solve related rates problems. And here's what we really are going to have to realize. These types of problems are going to tie into this idea. Any quantity that is changing, could be getting bigger, could be getting smaller. Any quantity that is changing is a function of time. So very often we think of functions of x, but we're really going to latch on to this idea that no matter what we're looking at in some of these problems, if our quantity is getting larger or smaller, it's a function of time. And furthermore, if a quantity is getting bigger, if a quantity is increasing, it's getting bigger, its related rate is positive. So we might be looking at area getting larger, a side length getting larger, a distance that a vehicle is traveling. If it's getting larger, its related rate with respect to time is positive. Likewise, now notice what I'm going to do here. Rather than have to copy everything, I'm just going to put these little tick marks here. It's saying if a quantity is, now I'm going to change. This way I don't have to write out every little word here. If a quantity is decreasing, its related rate is negative. We're going to see that a lot more in more detail. So related rate problems can be very broad. They can deal with all different types of problems, and we're going to see 4 different problems in this video right now. But the common theme is you're going to have quantities that are changing. They might get bigger, they might get smaller. They're functions of time. And of course, if our quantity is increasing, we have a positive related rate. So let's just read this together. It says the area of a triangle is increasing at a rate of 6 square inches per second. Just that word is implying that area is a function of time. But the related rate, we're going to write it with differentials here, dA dt, how area is changing with respect to time. That's what dA dt is actually saying. It's increasing, so it's positive 6 square inches per second. Okay? The base of the triangle is decreasing at a rate of 2 inches per second. So base, maybe I'll call that B, area I'm calling it A. dB dt, this is how my base is changing. I'm assuming it's a function of time, but it's decreasing, so it has a negative rate of change. Think of it this way. It's if we put in units, every second it loses 2 inches. It subtract 2 from it. That describes the change. So then they want us to find the rate at which the height is changing. So they're saying find, well, how is the height changing? It's a function of time. dH dt, find dH dt when the height is 10 and the base is 4. And I want to point out in related rate problems, you can have quantities that are changing all the time. And you know, this height being 10 inches, maybe that's just for the briefest split second, just for a brief instant. 1 instant later, it's going to be larger or smaller. Our base, at some point, it's going to be 4 inches, but what we're seeing is it's losing 2 inches per second. So 1 second later, it's going to be smaller. So it's only going to hit 4 inches for 1 split second. So of course, I think what is going to happen is students will correctly point out, well, I know the area of a triangle, one of the most famous formulas of all, 1/2 base times height. You could say A equals 1/2 B times H. But what I really, really, really want you to understand, this is so critical. Please realize that area is a function of time. The base is a function of time. The height is a function of time. Why am I so emphatic about this? We're going to see a lot of work taking derivatives with this perspective. And that can be so confusing if you don't realize that these are functions of time. Well, in any event, I'm going to take my derivative now, and I'm going to say, hey, I can go ahead and take my derivatives, and no doubt about it, I'm going to come over here and say dA dt, slide this down a little bit, this right here is the product rule. This right here is the product rule. You've got 2 functions of time. So I'm going to say I've got my 1/2, that stays out in front, but we'll have our u v prime. So keep my u the same, that's b. What's the derivative of h? Well, it's really looking green here. It's really h of t. So what's that derivative? dH dt. Now I'm going to say plus u prime. Well, what's the derivative of b? Well, b is a function of time. That's dB dt. I'm going to say times v, which is h. And wow, right now we can plug in so much information. We're going to say, look, I know that the rate of change for my area was 6, positive 6. My base momentarily, just for a split second, is going to be 4. I'm trying to find dH dt. I don't know what that is, honestly. I'm looking for it. dB dt. Well, dB dt was this -2. Remember, it was decreasing. And h was 10. They're saying for this brief split second, we're going to have that. So, look, I'm going to recopy this off to the side. And I'll get 6 is equal to 1/2 of 4 dH dt. I'm going to be able to solve for dH dt. -2 times 10 is -20. And tell you what, I'm going to distribute this 1/2, and I'll get a 2 dH dt. And 1/2 of 20 is going to be a 10. So I've got that minus 10. I'm going to add a 10. 6 plus 10 is 16. I'm going to divide by 2, and without too much work, we can see we've got dH dt is equal to 8, but let's use units. You see, our base was in inches, our area is in inches squared, so our height's going to be in inches, and this would be inches per second. This is saying that my height is going to be increasing. I've calculated a positive rate of change, a positive related rate. So every second, my height will have 8 inches added to it. So I hope this is helpful. Everything is a function of time. And we're going to proceed. We're going to go to some more problems. And what you're going to notice is, in general, you're going to have a situation described. Sometimes it's purely geometrical. Sometimes it's a situation that we have in the real world. And your goal will be to find an equation relating the quantities that are interacting and that are changing. Let's read example 2 together and see if we could make some sense here. It says, at noon, a car leaves point A, headed due north. It's got a constant speed of 20 miles per hour. Now, this looks like a rate, and it is. It indeed is. So, look, I'm going to start drawing a picture here. They don't give us a picture. Here's point A, and a car is going to go due north. Well, we want to have that go due north. Maybe we're going to have this. This is going up. I don't know how far it's going to drive. Let's call Y the distance that that car drives north. But once I know that, this is going to be an increasing distance. So dy dt is what I have. This is my rate of change. It's positive 20 miles per hour. Right? Watch out, this next part gets tricky. 1 hour later, another car leaves headed due east at a constant speed of 40. So all of a sudden, we're going to have this other car coming this way. It had a hour delay, or the northbound car had a 1 hour head start, if you'd like to look at it. But this length is going to grow. dx dt should be a positive. What's happening? It's positive 40 miles per hour. Every hour, we're going to add 40 miles to that distance. You'd say, well, wow, look at that. I've got this. Of course, there's a time delay. One other thing, we know that the directions are perpendicular when they are consecutive, as they are right here, north and east. They will make a right angle. But what is the rate of change? So find some rate of time of the distance between the cars. Well, the distance would be going from this point to this point. I'll call it D at 3 p.m. So find the rate of change of the distance. So really they're saying find, now this is going to sound funny, d dt, find how that distance is changing with respect to time at 3 p.m. Well, unlike our last problem, we don't have a very simplistic formula from geometry relating these three immediately to us. It's not like we have memorized, like we did up above, 1/2 base times height is the area of a triangle. But in this instance, we could see that we have one of the most famous relationships in a right triangle, and that would be the Pythagorean theorem. I'm going to say x squared plus y squared equals d squared. And please hear this. This is so critical. Every function here is a function of time. And that's really where I was coming up right here, just to drive this home. If your quantities are changing, they are functions of time. What am I really getting at? This is like having x of t squared plus y of t squared equals my distance function. Well, distance at any given time squared. Now, I'm writing it like this, and I'm even going to highlight it, because this next step can look so funny if we don't think of these quantities as functions of time. I'm going to take a derivative, and of course you always have to ask yourself, take the derivative with respect to what? Well, we're taking our derivative with respect to time. This is the chain rule. Look at this. Bring down the 2, you'll have 2x. Take the derivative of the inside. Wow, look at that. Come next, chain rule. Once again, bring that 2 down. And we could say, well, y of t, or we could just say y. Take the derivative of that inside, dy dt. Finally, we're on that right side. You'd say, oh, derivative of the outside, bring down the 2, and then you'd have d of t, or d, just to the first power, but take the derivative of the inside. Look at that. This is why related rates always come after the chain rule. You have to know the chain rule to be able to do related rates of change. Well, once we get here, I'm going to make a nice suggestion to divide by 2. Divide by 2 everything, both sides. Do you have to do this? No, certainly don't. But wow, it makes life so much easier. So much easier. Look at this. We've got all that. And I think at this point we might be feeling pretty good because kids can say, oh, look, we had a related rate up above. We know what dy dt is. We know what dx dt is. We're trying to find dd dt. But all of a sudden, we're going to feel very, very upset because we're going to look at this equation that I have right here. I'm going to put a little red star right by it right now, and kids will correctly say, well, you know, you've got 2 related rates. You've got dy dt and dx dt. We're missing a lot. We're missing so much. How in the world can we put this together? It doesn't seem like we can solve this problem. Well, I want to point out that there's a very, very, very famous formula in math and in physics that the distance traveled is your rate of speed times time. Distance is rate times time. You can think, well, how does that come into play? Well, let's take a look at the distance north. Let's just take a look at your distance going north. How fast was that car going north? Well, they're going at a constant speed of 20. How many hours were they driving? Well, they start at noon and then they go to 3, and I think you could see pretty quickly here, as you're looking at that, that's going to be 3 hours, right? So the distance that you're going to travel to the north is 60 miles. Guess what, though? We're calling that y. Y equals 60. Likewise, we could say, well, what about your distance going to the east? Well, what's their rate? As we read in here, it says another car heading east is going a constant 40 miles per hour. But how many hours are they traveling? Well, they left 1 hour later. That's where that comes into play. And you could see at a clock, here's 1, and we want to know what's happening here. You can see that they're just going to have 2 hours. They're just going to have 2 hours. So 40 times 2 is 80. That's your distance that this car has traveled. That's what we could call x. Well, right now, you could probably feel a great sense of relief. You could say, well, now I know what x is. You know, I can come over here and I can say, hey, x is 80. And I know what dx dt is from right here. That's 40. And you could happily say, well, y, you just found that to be 60. And dy dt right at the top of the screen is 20. And kids will say, oh, this is so great. Now you just have to find dd dt, how your distance is changing with respect to time. But oh my gosh, we've got to find d. And all of a sudden, we can feel very, very, very upset and say, well, wait a minute, how in the world do you do that? Well, let's revisit this triangle just for a moment. Look at x. X, we saw just a second ago, was 80, right? That's right here. What about y? At 3 o'clock, y was 60. That's what we just plugged in. And then you could say, could you find the distance between them? Well, there are a number of ways we could do this. We could do the Pythagorean theorem. We definitely can do that. That would be always a correct move. But I'd like to remind you of Pythagorean triples, the most famous of which is the 3, 4, 5. And it sure looks like that would relate here. You might remember from AGT. In a 3, 4, 5 right triangle, if you were to take any multiple of the two sides, you'd have a multiple of the third. So look, it looks like we're multiplying 3 by 20, 4 by 20. 5 would get multiplied by 20. D would be 100. Wow. So could you do the Pythagorean theorem? You bet you could. But these triples, oh my gosh. We'll talk in class about the Pythagorean triples and how they can help you out. Well, now we just have to solve for d dt. Tell you what, let's see if we can do that real quickly. I'm going to divide everything by 100. I want to show you something cool. Dividing by 100, look, this 0 and this 0 cancel out. This 0 and this 0 cancel out. What are you left with? 8 times 4 is 32. 6 times 2 is 12. And wow, then we just have our dt. Looks like we're going to get 44. dt is 44. And what are our units? Always put units in. That's miles per hour. That's how the distance between the two vehicles is changing at 3 p.m. Well, I hope this is making some sense for you. Let's actually... Okay, sorry about that. We had a little technology glitch with moving on to that second page, if you saw the jump. Let's flip to the back and take a look at example 3. It's dealing with a ladder, and a ladder 10 feet long. So a ladder 10 feet long rests against a vertical wall. So, we've got our wall right here. Got our ladder coming over here. By the way, the ladder is fixed. This is 10 feet, and it's not going to change. It's always going to be 10 feet in this problem. Sometimes that's the huge part of what we've got to deal with. The bottom of the ladder slides away at a rate of 1 foot per second. Well, the bottom of the ladder, if I may, I'm going to just maybe highlight that in yellow right here. Let's call that x, okay? And dx dt, ask yourself, as this ladder slides away, is this distance going to get bigger or smaller? You can see it's sliding away, that x is going to grow. It's a positive 1 foot per second, right? So we've got that. So if the bottom of the ladder slides away, how fast is the top of the ladder sliding down? Well, here's why. It'd be so many feet above the ground. So find dy dt when the bottom of the ladder, when x is 6 feet from the wall. So, wow, just real quickly, I hope we can see that again. We're looking for an equation to relate the 3 sides together. We're going to choose the Pythagorean theorem. It's not true that every problem has the Pythagorean theorem. That's definitely not the case. It does show up from time to time. It's one of the most famous theorems in geometry. But notice that the right-hand side, it's a quantity that doesn't change. So I'm not writing it as a function of time. I'm just writing it as a constant. So let's take our derivative real quickly. Chain rule. This is going to be 2x dx dt. Bring down a 2 here. We'll have a 2y dy dt. And 10 squared is 100, but what's the derivative of 100 of any constant? You're going to get 0. You're going to get 0. And again, just like we did before, you can divide by 2. Now, if you divide by 2, I think you guys can see pretty quickly, you're going to be left with this. So, we're getting there. We know dx dt is a positive 1. we know x is going to equal a 6. And we're trying to find dy dt, but we don't know what y is. Well, again, just for the briefest of moments, this x right here could be a 6, just for a brief second. This ladder is still going to be a 10, and then you could say, well, what's y? Well, do the Pythagorean theorem, or look for a Pythagorean triple. By the way, those are like 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40, 41. You might remember these. But look for a multiple of them. Sometimes you'll be in good hands to see that. Look at that, 3, 4, 5. If I double that, I'd get a 6, 8, 10. Wow. Hey, that's pretty nice. Y would have to be 8. So I'm going to, real quickly, plug in the 8 right here and then solve for dy dt. Well, 6 times 1 is just a 6. And then we just solve for dy dt. We can subtract our 6, divide by 8, and don't forget, let's put in units here. Reduce if you can. That's going to get you negative 3/4. But negative 3/4, let's think about this. It's going to be feet. Everything was in feet, and it would be per second. And this would indicate that that quantity is decreasing, which is what you would expect. If you saw this ladder, what's going to happen? If it's sliding down, a little bit later it's going to look like this. If the base of it's sliding out, what's just happened with that vertical distance from the top of the ladder to the floor? It's dropped, right? It's going down. And that's what this dy dt is really going to show. All right, one last one. You can see that really we've got so many different types of questions that we can be dealing with. Last one is a shadow problem. Let's do this together quickly. Tina is 4 feet tall, and she's moving away from a 10-foot tall light, the lamp source. So we can say here's 10 feet. Here's Tina. Tina's right here. She's 4 feet. And she's moving away from it. So here's her distance. And she's moving away. And by the way, Tina's standing up straight, making a right angle with the ground. So is the lamp. She's walking away at 4 feet per second. So this x right here is going to be getting bigger. She's walking away from it. It would be positive. If she was walking towards it, it would be negative. That distance would be getting smaller and decreasing. But how fast is the length of her shadow changing? Well, her shadow is right here. I'm going to call this y. And it's formed by the light being blocked by her body. Right? And that's why, when you look at the shadow, it's always the shape of your body, but it's where the light is being blocked. So, of course, y is the length of that shadow. So how fast is the length of the shadow changing? So find dy dt. We're going to assume that x and y are functions of time when she is 10 feet from the lamppost, when x is equal to 10. Well, right now it can be tempting to want to do the Pythagorean theorem, but I think it's pretty evident that the Pythagorean theorem doesn't apply here. We don't have a distance of the hypotenuse coming into play here. And what we do instead is, again, you can have very different methods, different equations at times. Look at this. Here's what's happening. Here is a triangle that Tina has. She is 4 feet tall. Here is her shadow. And here's this angle that the light is making with the ground. But let's also look at this larger triangle. And in this larger triangle, we could say, well, let's see, that's 10 feet. Look at this base down here. You would add, this would become x plus y. And again, same angle right over here. You might remember when you have angle, angle in geometry, you have similar triangles. These are similar triangles. So we've got angle, angle here. So what can we do? We can say 4 goes with 10, just as y, this base, would compare to x plus y. And again, these are all functions of time. I'm not going to take a derivative just yet. In fact, I'm going to cross multiply. I'll have 4 times x plus y. Over here, I'll have 10 times y. And let's see what we'd have. This is 4x plus 4y equals 10y. And tell you what, I'm going to subtract a 4y. And I'll have 4x equals 6y. So I'm going to bring that back up here just so that we can see it with this perspective that we had with our information. Now that I've got an equation, I'm going to take my derivative. Notice I didn't take my derivative earlier. I didn't want to have to deal with quotient rules and real messy derivatives at that. Well, what's the derivative of x? It's really x of t. We'd say it's dx dt. How about the derivative of y? Well, it's just dy dt. And look at this. dx dt is 4. And oh my gosh, you don't even need to plug in the fact that we want when she is 10 feet away. This is 16 equals 6 dy dt. We're going to divide by a 6. And 16 divided by 6, if we were to divide out a 2, we'll get 8/3. So that's 8/3 feet per second. It's a positive rate of change. Her shadow is growing. So that's it for the related rates lesson. We're going to continue to review it and get you some practice on it. But hope that made sense. We'll see you soon.